In this lecture, I'm going to introduce the probabilistic programming language Stan so that we can start coding in Stan proper. Until now, we've been using BRMS, but we're going to now start using the actual programming language. BRMS just produces Stan code in the background and runs it. So it's just an easy syntactic sugary kind of front end, but to do more advanced modeling, you're going to have to get your hands dirty with Stan programming language. So let's talk about that. Well, here's the textbook again, and you should read the chapter because there's more detail there that I will not discuss in much. I won't elaborate on it much. So basically, as you probably know, there are many probabilistic programming languages. In the beginning, there was, I think the very first one was WinBugs, and from that emerged another programming language called Bugs. And I think Bugs stands for Bayesian uncertainty using Gibbs, or Bayes using Gibbs sampling, something like that, right? And then, so WinBugs was pretty difficult to use, and that's putting it mildly. And eventually, Martin Plummer, who was a cancer researcher in France, he implemented just another Gibbs sampler, JAGS, which for a long time played a very important role in disseminating Bayes. And in fact, back in 2012, when I first started doing Bayesian modeling, I was doing only JAGS modeling. I tried to use WinBugs, but A, I don't have a Windows machine, and B, even if I had a Windows machine, it was a very messy piece of software. So there are other pieces of other programming languages available now, which are of course really very advanced. So PyMC is an important one if you are a Python user, and many of my students and some of my postdocs even use um, Python and MC, Monte Carlo sampling there. And there's also another programming language that I never actually got around to learning that could be very interesting too, or INLA. It's worth looking into that as well, because one of the things that it does well is spatiotemporal modeling. So like if you want to model variation over time as well as space, that's a good programming language to work with. There's also Turing, which I believe is in Julia. I'm not sure about that. But there are several languages like this. There might be even more now, I don't know. But we are going to be using Stan because of the many advantages that it affords for the kinds of problems that I'm going to discuss in this course. So one of the key ideas here is that we are going to use Bayes' rule, of course, right? We have a likelihood function. Big theta is a vector of parameters usually. It could be hundreds of parameters. Okay, so that's where the complexity begins when you've got so many parameters like in hierarchical models. Then you have the priors on the parameters, and you use Bayes' rule to get the posteriors given the data. And for that, the big complication is the denominator, the normalizing constant, as I discussed last semester in chapter 2, I believe I discussed this in the lecture for chapter 2, that computing that normalizing constant or marginalizing out the parameters can get intractable if you have hundreds of parameters. So one often works with the unnormalized. So this is the normalizing constant. So if you drop the denominator, then you're working with the unnormalized posterior. And this unnormalized posterior, which is written as Q here, this will become important in Stan in a moment, is proportional to the posterior distribution, but it's not exactly the same thing, of course, right? Because of the absence of the normalizing constant. So once you put the normalizing constant on a posterior distribution, the height of that distribution will change because the point of the normalizing constant is to ensure that the area under the curve sums up to 1. Okay, so um, as you may remember from my lecture on sampling, I will put up this lecture, a link to this lecture again. There, what we are using instead is Hamiltonian Monte Carlo, and there, what Hamiltonian Monte Carlo does is that if you have a posterior distribution like this, shaped like this, it flips it, right? So it just becomes a valley, and within that valley, the sampler is um, is basically moving an ice puck, right? And because the shape of the valley is the way it is, most of the samples will come from the high density region, and only rarely will you get samples from the tails of the distributions, right? So that's in the lecture on sampling algorithms, which you can look at to review later on. Right. So what Stan is doing is that it's taking the negative log of the unnormalized posterior, right? So this is the unnormalized posterior, this one here, right? It's taking the negative log of that, and that means it's flipping it over, right? So it becomes a valley, and so that's how the sampling is happening. We're getting samples from that posterior, unnormalized posterior distribution, okay? All right, so the unnormalized posterior distribution per se is not going to allow us to figure out the summary statistics that we need to draw our statistical inferences. And so that's why we end up needing samples from that distribution. And so those samples that we get, those samples are then used for computing the summary statistics. I mean, even though the R norm function is producing samples from a normalized density, I could still write a function removing the normalizing constant from the definition of the normal distribution, and then I could take samples from that distribution using one of the sampling methods, that I discussed in my lecture. So I mean, but just to illustrate like what samples look like, here I'm taking 1,000 samples from a standard normal distribution. So this could be for some theta parameter, right? So once I have, let's take even larger samples. So once I have like a large number of samples, I can compute summary statistics on this, right? So I could compute the 5 or 6 number, whatever it's called, summary, right? So 1, 2, 3, 4, 5, 6. Yeah, I knew it was 6 numbers. So you can get the mean is close to 0, as you would expect from a standard normal distribution, and probably the standard deviation is also close to 1, right? So standard deviation of theta is also close to 1. So you can get summary statistics. You can also compute 95% credible intervals now from these samples, right? So that's the point, actually, just a quick version, of why we need these samples and what they're good for. So So here we are just illustrating, what it would mean. So suppose um, um, suppose we are getting data from a normal distribution with a particular mean and standard deviation. This is random data, and suppose we have defined some priors on the parameters mu and sigma. So, I mean, so this is kind of weird, okay? Because um, no, it's not really weird. Sorry, I got confused myself. But basically, we are getting data from some normal distribution with some mean, some standard deviation, and we define some priors for mu and sigma, not knowing what the true values of mu, mean, and standard deviation are. That's why I got momentarily confused here. So uh, we have these priors. Now we're going to be um, working with this rule here, or the unnormalized posterior. We have the likelihood, we have the priors for the parameters, and so we're going to multiply those guys out using Bayes' rule, right? So what would that look like? What that would look like is that the unnormalized posteriors for mu and sigma, given the data, would be the product of the likelihood and for all those 100 points, hence the product term here, okay? Y sub n is the 100 data points multiplied with the two priors here, okay? So, like we could even like come up with a function that actually allows us to, you know, produce this here, okay? So once once I've figured out the unnormalized posterior, I can visualize it because I just wrote a function that computes it. And so if you just plug in, you take the unnormalized posterior distribution and set some particular values for mu and sigma given the data that we just simulated. This is what the unnormalized posterior for mu and for sigma will look like. So it's a joint posterior distribution, right? So if you have hundreds of parameters, you will have a 100-dimensional space, right? Hundreds of dimensions in the space. Right. So as discussed also in the textbook, the shape alone of the normalized posterior density, this one here, is not enough for us to figure out the summary statistics, right, over the credible interval and so on. So that's why what HMC does, Hamilton Monte Carlo does, is that it generates samples from from that unnormalized posterior, and it gives a joint posterior rather, and it gives you samples that you can use to compute summary statistics, right? So that's what all this big discussion is about. One could do this on the log scale also, right? So basically, instead of multiplying the terms, you take the log of the likelihood function, you take the log of the prior, and you end up with the log unnormalized posterior density, okay? This is easier to do computationally, so that's what Stan actually does, right? So, so in our case, it would look like this. We have again 100 data points on mu and sigma here. Here's the prior on mu, and here's the prior on sigma, and we're taking the log of everything. So instead of multiplying, we're adding stuff here. Okay. So the Stan syntax is actually always stored. Stan is the program itself is stored as a .stan file. That's the extension, and there will always be um, several blocks in the Stan code, right? So a piece of code in Stan is defined in blocks, which I'll just show you examples of. And um, each block will contain information about a particular type of object that we're interested in or we're working with here. So I will come back to this in a moment. Okay, so let me just show you the code. So for example, what the first block usually, not always, but usually the first block in a Stan model is the data block, where in curly braces you define several variables that are relevant for the modeling task at hand. And notice that every line will always end with a semicolon. Well, that's because all this code will be translated to C++, and C++ uses semicolons to end a line. And also every object, like this object here and this one here, they will have to have a type defined for them. So for example, n is the number of data points. It has a lower bound of 1 and it's of type integer. Y is a vector containing n data points, capital N data points. And so vector is the type of this object here. So that's how you define the data block. Okay. I mean, of course, later on there'll be much more information in the data block, but this is just a simple example. The next block will indicate what the parameters are. Sorry, my cat wants out. Sorry about that. So the next block is the parameters block, which is also in curly braces. Every block will be in curly braces. And the two parameters are, of course, mu and sigma. They're both of type real, and sigma is bounded on the left by 0, so it can't be negative. So you're constraining the parameter here. Okay? That's how you constrain the parameter. You give the type real, and then you put in angle brackets what the lower bound is, or upper bound. Okay, I've never used that, but sure, it could be. Okay. So you could put lower equal to 0 and comma, and upper equal to whatever is relevant for your problem. All right, so finally the model, there'll be a third block at least, that's called the model, and that contains the specification of the priors and the specification of the likelihood. So let's first look at the specification of the likelihood. What it says is that for every row in the data frame, what we are doing is that we are defining a log of the normal probability density function, which has parameters mu and sigma. Right? So this statement here is actually very similar to what you're familiar with in the course. So like I would often write, right, in the textbook, for example, I would write mu sigma like this, right, to represent the underlying distribution that's producing the data, right? So you should read this syntax. I will explain this a bit more, but this L is the log. This is the normal probability density function. So the log of the normal probability density function, and y sub I is representing each of the data points. So this for loop is actually going to run for whatever the length of the data frame is, and it will be getting samples for mu and sigma, and as a consequence from the priors, which I'll just describe, and then you'll be modeling this data as a function of those parameters. Okay, so I'll just get to this point here. So that's the likelihood function here. So normally, this for loop would be put in curly braces, but here it's not. There are no curly braces around the beginning and end of the for loop. That's because it's just one line, So you can drop the curly braces if it's just one line, but if it's more than one line, then you have to put those curly braces. They're not optional then, right? So now that's the likelihood. Then the priors are the same kind of shape. So mu is coming from a normal distribution with mean 0 and standard deviation 20. So this is like writing, right? Mu is coming from a normal with standard deviation 0, mean 0 and standard deviation 20, right? And similarly, here we have a log normal PDF that's for the sigma with parameters on the log scale that are 3 and 1. So now the big mystery here is this weird syntax, right? This target syntax. Okay? So target is a reserved word in Stan, and what it does is that it adds all the terms, in the unnormalized uh, log posterior, right? The summation that I showed you earlier, it adds those terms to incrementally to the unnormalized log posterior density, right? Just keeps adding those density values, which I will just explain in more detail. Um, so the addition is happening because it's on the log scale. That's the only reason. Okay. All right. So let's look at what target does. Okay. So let's think about one iteration. So one hypothetical iteration of the sampler. Okay. So we have a stand model here. Sorry, this one. Normal.stan in the bcogsci package. So you can extract it, save it as the object normal, and you can generate some simulated data here. There we're generating the simulated data. Save it as a list. So in Stan, the data are not entered as a data frame type like in R, but they are entered in as a list type. So this is R syntax actually. So in R, we are writing in R right now, and we are producing a list type which contains a vector y, which is the data, and this n is the length of the vector y. Notice this lowercase y and n, they turn up in the Stan model earlier. Lowercase y and capital N. That's where they're defined in the model, and we're going to feed those variables into the Stan model. Right, so and that will be fed in through this list object now, okay, into the Stan model. So the code itself is easy. Like this is the Stan model that I just extracted from the bcogsci package, and this is my list object data, and so you can fit the model. And so what's going on now, okay, with this target thing, this weird target syntax? So if the model is running, let's say for 4,000 iterations, right? Each of those iterations, mu and sigma are going to get some particular value. So let's say I have 4,000 simulations, mu and sigma are going to get 4,000 sets of values. Okay. And the choice of those values is done through the Hamiltonian Monte Carlo sampler. So whenever the ice puck stops, that's a sample, okay, in the two-dimensional parameter space. So suppose that in an iteration, we get one particular value for mu and one particular value for sigma. Just an arbitrary example, okay? So now we have these samples. In the model block, in this model block, what's going to happen? So I'm going to explain now what the functionality of this target thing is, okay? So what will happen in the model block is that at the very beginning, before anything has started, before the sampling has started, target will have value 0. Okay. Oh, and I should also mention that this syntax should probably be familiar to anyone, who's done some programming. This is just incrementally adding more and more values to a particular variable. Okay. So one thing, this is a side note, okay? So one thing is that the um, sigma parameter is constrained to be positive, but the actual sampling that's happening is automatically done by Stan, such that the sampling of the sigma parameter is in an unconstrained space. That's just convenient for the sampler. And then it back transforms it back by exponentiating, to get back the, it converts it to the log scale, samples from all over the place, and then exponentiates it back into the original scale. Okay. So that's happening in the background. End of side note. Okay. So yeah, this is just explaining what I just said. So that's not super useful. Oh yeah, there's also one other important detail here, which is also a side note, that when you make these kinds of transformations, you have to do something called a Jacobian. You have to put in a Jacobian. And that has to do with calculus. You might have encountered the Jacobian in transformations. We will talk about that later on in the course. Okay, so we will discuss that later. So right now, let's ignore all those details. There has to be some transformation done, and some correction has to be done, and that correction is called the Jacobian adjustment, and we'll discuss that later. It's not important right now. Okay? What's important is that we are starting with a target value of 0, and our first samples that we're going to get for the parameters will be these two numbers for mu and sigma, 3.15, 10.67 respectively. Okay. Right. So we had this value 3.15 blah 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 for the mu parameter. We can now calculate the log of the density for this particular sample value for the prior that we had defined here. So like if the sample that we got was this one here, in with d norm I could do this, in R could just d norm. What's the value of this this sample value when the normal distribution has mean 0 standard deviation 20, right? If I take the log of that, right, I get this number here. So after the code reaches this point, so we are here. Okay, sorry, let me just go back to we are at this point in the model. In the very first iteration, target is the value, has the value 0. So what the model is going to do is, or what what Stan's going to do is that it's going to evaluate the log of the density of this distribution evaluated at that particular sample value. And this number is added to target. So target was 0, and now we've added 0 plus whatever that number was. What did I say it was? Right, minus 3.92. Oh, there we go. Here it is, right? That's that number. That's where it came from. So this is now added to target. Target's value is not 0 anymore. It's minus 3.92. Now, oh, and this number here, where did this number come from? Right? This number is the Jacobian determinant. It's the Jacobian adjustment that I mentioned earlier. Because of the back and forth transform of the sigma, God, this is so horrible, right? So because of the back and forth transform of the sigma, we have to put that Jacobian in, and that's what that number is. Okay, so we end up with minus 1.55, right? Well, then we come to the next line, which is target plus equal to log normal LPDF, and then sigma 3.1. And what that does is the same thing again, right? So let's go. Suppose what is our observed sample value of sigma? It was this number here. So I'm going to go back. I'm going to figure out, is it L norm, D, L norm or something for this number with values 3 and 1. I think I had chosen, right? What was it? Yeah, 3 and 1, right? So we compute that number, but we take the log of that. Right? So minus 3.48. So where was I? Sorry, I got lost here. All right, so we have the first log density of mu, Jacobian adjustment for sigma. We end up with this number here. Then we reach this point, and after we reach this point, we add the log of the density of the log normal evaluated at this number, which turns out to be what? Let's look here. Which is equal to minus 3.498. Minus 3.48. Is that the number I also got? Yeah, that's also the number I got, right? So now we got this number here, and so target will now be updated to whatever its last value was, which was minus 1.55 here, right? To minus 1.55 plus minus 3.4. So now we are at minus 5.04. And the next part of the code will run a for loop for n data points. Okay. And for each iteration of that for loop, we are going to add to the target value, which is currently at minus 5.04, the log density of the normal distribution with those sampled values that we had at the beginning of this whole iteration, evaluated at each of the values of y. So if there are 100 values, we're going to be summing up the log density of all the values. And the code for that in R is shown here, right? If this was a vector of 100 values, add these mean and standard deviation values on the log scale, log equal to true. I'm summing up all the log densities. That gives us a number minus 371. And what we end up doing is we are adding to minus 5.04 here. We are adding this thing. That's the end of one iteration. So we're going to do this 399 3,999 times, right? If it's 4,000 simulations, 4,000 iterations. On the next iteration, there will be a different sample for mu and for sigma. So what this whole process gave us is that it told us that the height of the unnormalized posterior at this end of this first iteration is the exponent of whatever this target value is. Right? So if we exponentiate this value, we get the height of that of the unnormalized posterior here. And this information is actually returned in the value of target is returned in this object called LP underscore underscore, which you might have seen and wondered about in the early part of this course. So you can also print out the value of target, but actually I've never done this. I mean, Bruno probably did this. So you can use it for troubleshooting, right? But I've never done that, I must say. Okay, so this syntax, this target plus equal syntax, I hope it gives you a flavor of what it's actually doing. And the syntax is actually quite similar to our sampling statements that we've been familiar with in mathematics and in statistics, but it's holding the log of the posterior density as the samples are going through. So what this means is that if there are 4,000 iterations, for each of the iterations, I'm going to get each of those 4,000 iterations, I'm going to get a particular number here, which I will exponentiate, and that number will give me the height of the unnormalized posterior for mu and sigma. This is the Q function I started with. Right? So this target syntax is the Q function that we mentioned at the beginning of the notes. Okay. So there are some comparisons here between the tilde notation that we are familiar with and target, but it's not important for us because what's important is to understand what target is doing, and we get that now, right? So we are going to be using this target syntax from this point onwards. You can use this syntax in Stan. It's not going to object, but there are some disadvantages, especially when you're using Bayes factors and doing k-fold cross validation. So you can read the details about that in the chapter and also in these notes here. You can read all this later, okay? So I'm not going to discuss this part here. I just wanted to get across the idea of this, the target syntax, what it does. That's important to understand. So I'm skipping all this. One thing that you can do that makes your life maybe a bit easier is to instead of using the for loop that we had used earlier for the end data points, you can just vectorize the whole operation, right? It gives you the same result. So here's a vectorized version of that, okay? So instead of writing the for loop, this is anyway a vector, right? So it's going to do everything that I just said earlier. All right, so that's the basic setup for the example here. So again, here's the simulated data saved as a list now, and then we run the model, Stan model, right? Then you can look at the trace plots of mu and sigma. Now you're seeing those, the the samples, in four independent chains for each parameter. You're seeing the distributions of the samples. So most of them are centered around, for mu around 4, and for this around 9, right? So you can see that they're sitting on top of each other, the chains, so they're converging. And you can also print out the summary, okay, for mu and sigma, and you see that you get a posterior, the summary of the posterior distribution, which is what you need, right, for inferential statistics. You can plot using MCMC hist. So all the things we learned in the early chapters will now be usable here after fitting the stand model. Okay. Right. So you can also get the samples themselves, like if you want to plot them yourself. So you can see, look here, there are 4,000 samples, right, for mu and 4,000 for sigma. So you can extract those guys actually. It's no, and use them, for your own. And here's your LP underscore, right? So there are 4,000 iterations. Remember? So I was talking about this example here. So these are the numbers that the correspond to the log posterior, unnormalized posterior density in those 4,000 iterations, right? And that tells you the shape of the posterior, the unnormalized log posterior density. Right. So this is just different ways of like looking at the different details here. The next topic that I will cover is looking at a simple example where we investigate close probability using STAN, but this time with the binomial likelihood. So the next example that I want to talk about is also a very simple one, but it gets us into the flow for fitting STAN models, is a binomial example. So suppose we want to estimate the close probability of producing a particular word. The sentence that you might hear is, it's raining and I want to go I want to take my X with me. So X would be either a word like umbrella, raincoat, something like that, right? So if you get people to fill in that missing word, the missing X in the sentence, then they would produce a range of answers, and you might consider one answer to be the correct one, right? So the umbrella could be the correct answer. All of the answers would be wrong. So suppose you have 100 trials, and in 80 of those trials, people actually return umbrella as the missing word. So we'll assume a binomial likelihood. This is a standard model. You could have fit this without any computer, right? From chapter 2, we know that. So because we'll define a beta prior on the theta parameter and assume a binomial likelihood. So beta 4 prior is what we're assuming here. The data will look like this. We will have the total count, which would be 100, lower bound of 1, type integer, and the number of times that the correct answer was given would be k. So there's two numbers that go in as data in list type into this STAN model. Lower bound is 0, upper bound is n, because you can have between 0 and 100 correct responses, and k is the actually given response in that particular experiment. So that's my data block. Then comes the parameter block. There's only one parameter, theta, which is constrained to be between 0 and 1 and is of type real, right? And then the model. The model has just two lines. One is the prior specification, which is the beta prior, beta 4 prior on theta, using that same target syntax that I just explained. And then for the likelihood, we have binomial log probability mass function, YPMF, not PDF, is because it's discrete, with the number of successes or correct answers as a function of the total sample size and theta. Literally the mathematical statement of the model is written out in STAN. Okay. So set up the data. This is the data specification. K is 80, N is 100, and then you extract the binomial model, this model from the bcogsci package, and then you run it through STAN, the function STAN, in the RSTAN library, and then you give it as input the actual STAN model and the data as a list object, and then you can print the summaries, right? Here we are interested in the posterior distribution of theta, and you can see that the posterior distribution of theta is actually going to be basically the same as what we would have analytically worked out. Okay, you could plot it and so on, so it's all straightforward. So this is easy enough. The next thing that we'll discuss is regression models now in STAN. So this will now get increasingly complex, and later on we will build up to hierarchical models where things are going to get very hairy, but we won't get there yet. We'll just keep building regression models in STAN and then get back to the more complex models later. So the next topic that I'll cover is regression modeling in STAN. There are some interesting twists here, so it's worth discussing. So we'll first look at simple linear regression that we've seen before. This is the question about whether attentional load affects pupil size. So if you remember in an earlier chapter, what we had done is that we had different levels of attentional load, and we were measuring pupil size on some abstract scale, so the units are not known, right? So these are the data. This is the model, sorry. There are n data points, so each row in the data frame is assumed to be generated from a normal distribution. There's an intercept, and there's a slope that is modulated by centered load. And then there's, of course, the residual standard deviation. So the priors are clear. We've discussed them before, nothing to say here. And then the interesting thing now is the STAN version of this model. We can because pupil size is just a vector now, we can simply define in a single line how the entire vector is generated, so cell by cell, right? And the vector is affected by this information here: intercept, the vector of centered loads, and the beta parameter and sigma. So this is just the same thing as writing the for loop that we saw earlier, but it's a bit faster. Okay, so this for loop goes through all the n data points in the data frame, and the only difference now is that instead of writing pupil size as a vector, we write pupil size cell by cell, and then for every element in the vector centered load, we define an equation. Okay, so it's a bit slower, but for these data, there's not going to be a dramatic difference. Okay. One important thing to notice in the code is that you will see that in the code there is a normal prior defined for sigma that has a mean 0 and standard deviation 1000, but that normal prior is truncated. Now BRMS does this for you internally, so you never think about it, right? But in STAN you have to actually do the explicitly specify that the normal distribution is truncated. So what's happening here is that we're defining the prior for sigma here, and then we're subtracting from it the complement of the CDF on the log scale. So the log of the complement of the CDF. So that's why you have L, log, complement, and CDF, right? So at the point 0 and for the same distribution that we're talking about here. So what this is doing is that it's just renormalizing the truncated normal distribution. So if you remember, the one property of a probability density function is that you need to have the area under the curve summing up to 1. If you truncate a distribution, then the area is not going to sum up to 1. So you have to fix that, right? And that correction is this one here. So basically what's happening mathematically is that if we have some distribution, so in this case it's the normal, right, the untruncated normal, and we delimit the lower and upper bounds of the distribution. So we truncate the distribution. That's what that truncation here means. A is the lower bound, B is the upper bound of some distribution, in our case the normal. So what you have to do to renormalize the distribution such that the area under the curve of the truncated distribution sums to 1 is to divide by the this is the cumulative distribution function at B. So what does that mean? So if, for example, if we are talking about a normal distribution, the cumulative distribution function at some point B is P norm B, right? So what we are doing is we are subtracting from the cumulative distribution, the cumulative probability of getting B or something less than B, subtracting from that the cumulative probability of getting A or something less than that. So what is B and what is A in our case? B is infinity because the right edge of the truncated normal is going to infinity. A is 0. So we are calculating the total area under the curve between plus infinity and minus infinity. That's what this denominator is doing. So this corrects the this renormalizes the distribution. Okay. So in log space, this is a division here. So the division becomes a subtraction on log space. Notice that I'm taking the log of everything now. Okay. Log of this difference is here and the log of the numerator is here. And so we are just taking a difference now. So log of the normal distribution corresponds to normal LPDF in Stan. Okay. And the log of f of x, where x can be anything, is in Stan normal log CDF. Okay. So B, as I said, is infinity. So f of B is going to be 1 because we're going from plus infinity all the way to minus infinity. So that's 1. Okay. And then so what that means is that we end up dealing with the complement of the log CDF evaluated at a equal to 0 because this term here is 1 here, and now what we have is the complement. So we have the CDF at 0 here, what I've highlighted, and so the log of the complement of the CDF at 0, right? That's what this is. Log of the complement of the CDF at 0. Okay, so that's what that is. All right, so as usual, the data needs to be a list. So this is all set up now in this code. Here's the list data object, And in the data object, we've got the pupil size as a vector, we've got centered lower as a vector, number of rows in the data frame. Okay, so the stand model is pupil.stand. You'll find it in the bcogsci library. And once you fit the model in the usual way, you see the trace plots. Everything looks fine to me here. And you can look at the summary statistics, etc., etc., and plot the posteriors, all standard stuff, nothing new here. Um, so that's a pretty straightforward thing to present. The only important thing here that was new was this command here. When you truncate a distribution, you have to subtract the log of the complement of the CDF. Okay, for the reasons I explained. And this is a general thing. I mean, this is just a normal, but it could be some other distribution, continuous distribution. All right. So here, like this number here is the probability. What we're just calculating is the proportion for the slope parameter, which is telling you the effect of load. What's the probability that um, the posterior distribution of the slope parameter is greater than 0, right? It's almost 100% here. So most of the probability mass is shifted to the right of 0. Okay? So we can now produce prior or predictive, posterior predictive distributions in STAN in the following way. You can, of course, once you have the posterior samples, right? Or once you have defined the priors, you could just do that in R. I mean, you don't need STAN for this, right? But in STAN, you can do this too. And the way we will do this is by adding in the data block, we're going to add one switch, a 0 or 1 switch called only prior. If only prior is 1, then we are sampling only from the prior. If only prior is 0, we are sampling from the posterior distributions of the parameters. So the model is the same, nothing changes, everything is the same as before. The only thing new is there's this if statement here, which is new now. And this is saying that if only prior is false, and this is confusing, right? if this number is if this number is 1, then the negation of that is that it's 0. If this is 0, if you're sampling only from the prior, only prior is 1, this is 0, then this if command will not do anything. If we turn the switch to 0, if only prior is, we don't want to sample only from the prior, but we want posterior predictors, then the negation of that will be 1, and then this if command will execute. And what it's doing is, it's actually fitting the model. So that means it's generating the posteriors of the alpha, beta, and sigma parameters. So if this code executes, if only prior is 0, this code will execute. And then I'll have the posteriors for alpha, beta, and sigma. And therefore, in the generated quantities block, I can now produce using the normal random number generator function. I can produce the posterior distributions which are going to be saved in this array of length n. So remember, and they'll be real number values. Okay, so what this array is going to contain is, for each of the 4,000 samples we have for the 3 parameters in the model. So we'll have triplets of samples, 4,000 triplets of samples of the posteriors, right, of the 3 parameters. For each of those 4,000 triplets, we're going to generate n data points, capital N data points. So what this will look like, this thing, what it will look like is, it will have 4,000 triplets of samples, 4,000 triplets of samples of the posteriors, right, of the 3 parameters. For each of those 4,000 triplets, we're going to generate n data points, capital N data points. So what this will look like, this thing, what it will look like is, it will have Um, I've forgotten the order in which it shows up, but we can check that later. So the first column will be capital N data points generated from the first triplet. The second column will be capital N data points generated from the second triplet of posterior samples, and so on 4,000 times. So there will be 4,000 columns and capital N rows, right, in this array. So, and remember that when we are generating data, we are using the normal RNG pseudo-random number generator here. Okay. So the interesting thing about this code is that this code is going to generate either prior predictive data if only prior is set to 1, or it's going to generate posterior predictive data. So if only prior is set to 1, what will happen is that this if command will not execute. This if command is not going to execute. If the if command does not execute, the generated quantities will be relying only on the priors for these parameters. And so what we're going to get in the p size spread array is going to be prior predicted distributions. Okay, so that's just explaining what I just said, and now we're going to run the code. So only prior is 0 in this code, therefore we're going to get posterior predictors, right? So you can look at those. So there'll be, oh sorry, so in the column number of observations, number of samples. Oh, right. So what I said about the array, you need to transpose it. So there'll be the number of rows will represent the number of samples, so 4,000, and the number of columns will represent the n observations that will be generated, right? So um, so this will be a matrix eventually, right? Once we look at this. So here's the matrix. We are extracting from the fitted model the p size spread, p underscore size underscore pred posterior predictive array, and we are saving it here. And if you look at it, we see that it's 4,000 rows and 41 columns. Why 4,000? Because we have 4,000 samples for the posteriors, and by 41 columns because each time we're generating 41 data points. Then you can of course use the PP dense overlay plot, which we've done before, to compare with the observed data, and you can see that the posterior predicted data is pretty decent here. If you set only prior to 1, now you're going to get prior predicted data, and now this plot is going to look super different, or it should, I think, because the priors are pretty weird. So you might need to do some control parameters. You might have to change those because there might be some divergences and so on. So you can do that. Now, if you look at the prior predictive distributions, they look pretty wild, right, compared to the data. So as far as I can tell, yeah, it's really broadly spread out. Yeah. Okay, so that's the story with the simple linear regression. Now one other thing that we need to discuss is whether we have the different data types that are there in STAN. So that's what I will discuss in the next part of this lecture. So let's talk about the different data types that are important for us. in this course. So some of the data types are usable in linear algebra and some are not. And so the basic linear algebra types are vector, row vector, and matrix, and but not array, right? So array can't be used. So what you could do is that you could, if you want to define a one-dimensional n-size container containing real numbers, you could do that by writing array and the size of the container of type real and then the variable name, or you could say vector capital N, that's already a real number of type real number in each cell and then the same variable, or you could use row vector n with the name of the variable, right? You can also define n1 times n2 size containers um, in the following way. So you can, with the array type, you can have n rows, n1 rows, n2 columns of type real in this object M, or you could use a matrix type, which is a linear algebra type. N1, N2 are the rows and columns specification, and then the name of the variable. And so you could also create an array with n1 elements and then vectors n2 in each of those. So that also creates a multi-dimensional or two-dimensional array. Two-dimensional array, yes. And then finally, instead of vector, you could use row vector, right? So the impact of these choices is whether you can do matrix algebra with them and how fast the model works. So we will see examples of this. I just wanted to mention that these types are available. So when you define the right side of the linear model, and you want to save it as a variable mu, then you have to save it because this is a vector, right? So you're going to save it as a one-dimensional container that is of type vector. Okay. Um, so you could convert a type vector. This was type vector, which I just showed you, into an array, but it wouldn't really buy you anything. So it's possible to do this kind of stuff, but we won't be doing it. Okay. All right. So when you do in the generated quantities block, you use the RNG functions, the um, the predicted values that will be generated from the prior or the posterior, like I discussed earlier, would have to be saved in type array. Okay. But if you use a for loop to generate prior posterior predictive data, you can define a vector and then with n elements and then fill those up cell-wise. Okay. So these are two options available. Most of the time we are using this actually in the code that you will see. Except for some exceptions later on. So the user's guide, Stan user's guide on mc-stan.org will of course need to be consulted as you get into deeper into coding, right? Now, the next topic is interactions, and this is where things get interesting. That's where the matrix type can become very useful because when you have multiple predictors like two main effects and an interaction, it becomes pretty tedious to write down the code for every slope that you've got and priors for every slope and so on. So this would be the standard way, that you would keep extending the model in BRMS, for example, right? That's how you would do it. you would have the main effect of load, of trial, and then the interaction between them. So now you've got three slopes, right? So you would have to define three priors, and then everything else is as before. Um, so we could write such a model, right? So in this upcoming model that you see here, you see that you define each of the betas, and then you go ahead and just state the model as before. One thing to notice here is this this dot product um, um, function in stan is different, is new actually. So what this is doing is, if you got a vector with n elements, another vector with n elements, it's going to cell wise multiply those two vectors, right? So it's not going to do a matrix multiplication. Okay, now here you've got a vector as well, but we are still using the star notation here to multiply, because this is just a scalar, right? So but this is actually, this star actually represents in stan, it indicates matrix multiplication. Now in matrix multiplication, multiplying a matrix with a scalar, it can be considered matrix multiplication, so this is not harmful. But here what we want is cell-wise products, right? Row by row in the data frame, we want cell-wise product, so we are forced to use the dot asterisk command. In R this is different, right? In R the star is the cell-wise multiplication, and matrix multiplication has its own special symbol, percentage star percentage. So you have to, don't be confused by this. This is matrix multiplication, this is cell-wise multiplication. Okay, so that's something new. But now what we can do is, instead of writing writing out the model for every term one by one, and then defining a prior for every term for the intercept and slopes, what we can do is, we can treat beta as a vector and just define a single prior for all three elements in the vector, and then set up the linear model in matrix form. Okay, so we've got, here we are keeping the intercept separate, so this model matrix doesn't contain any intercept. So normally you, in the introduction, when I talked about, in contrast coding, I talked about the matrix formulation of the linear model. The design matrix contains ones in the first column, and the vector for the parameters contains the intercept. But if you have the intercept separately, then the design matrix contains only the columns representing the predictors, right? So that will have an impact in a moment. Okay, you'll see. So now we made a matrix version of the linear model. That simplifies our life, because the slope parameters now have all the same uninformative priors. And so here's what changes. Okay, in the data block, there's a matrix type that is introduced now. So that's why we talked about data types earlier. N rows. Why n rows? Because there are n different data points. Okay, that's that n. And what is k? K is the number of predictors. So this is 3 in our case, right? So it's an n times k matrix, no intercept, okay, in this data, in this model matrix, and then the vector for data. So what we are doing now, what changes is that we still have a single scalar for the intercept, but for the three betas, we now have a vector. So the first element will contain beta 1, second element contains beta 2, third element beta 3, right? So now we can write the model in matrix form. So let me get to this last line here. This is the important line. So we're using the normal LPDF function. Pupil size is being generated from this model, And so we have alpha plus x star beta, so matrix multiplication. This time there's an actual matrix multiplication because this is an n times k matrix and this is a k times 1 um, um, matrix, right? K times 1. So 3 times 1. So the rest is basically the same, except here we've got for the entire vector beta, which contains k elements, k is equal to 3, we are defining a single prior. So that makes it more compact and works faster as well. So there is actually a built-in function um, in Stan that makes all this even more compact, right? So you can write, instead of normal LPDF, you can write normal ID GLM LPDF, and then pupil size as a function of the all the all the you know the not the parameters but the all the inputs that go into that this function here. Okay, so this will do the same thing as this here. Could be a bit faster, but I mean this is really a simple model, so I'm not sure if you really need it, but this will show up occasionally so you know what it means, right? You can use these built-in optimizations that actually do the set up the generalized linear model for you, you know, general linear model for you. Okay, so in bcogsci, in the bcogsci package, there's the pupil int.stand model that you can look at that includes this last statement. Okay, so you can play with it a bit. Yeah, so uh, how would you create the X matrix? What you can do is, here we are just centering trial and load, but here's the command. There's a function called model.matrix that says that that create a matrix with the main effect of load, the main effect of trial, and its interaction. So this is just this is our code. Okay, this is just a shortcut in R for defining main effects and interactions. So we are just writing 3 terms in one shot here. Main effect of center load, main effect of trial, and the interaction. One could have expanded this, you know. You could write this out like this. If you want to make it more transparent or something. Right? Oh, sorry, I didn't mean to do that. So, right, so here, oh, sorry, I don't have DFPL. This is from an earlier chapter, okay? So when I write, oh, I did not center load. God, this is horrible. So what does this thing look like? Okay, I'm just going to use the code that they provide here, right? That Bruno wrote. So I have to install library tidybus, and now this should work. Okay, so I've centered everything, and now I should be able to produce my design matrix. So this design matrix looks like this now. It contains main effect of center load, main effect of trial, and the interaction. I could have produced exactly the same thing by writing the following: main effect of this and this plus colon. Right, so the star notation in R is shorthand for this notation, right? So if I look at X now, it's exactly the same thing. There's exactly the same setup here. Right, so coming back to this. So we've set up the model matrix. This goes into the data object as a matrix. Okay, so it's n times k. And then I have all the information about k and n here, and then the vector of data. And then we fit the model using the pupil int model in bcogSci. And if you look at the output, you get the posteriors. Pretty straightforward, right? So what this shows you is how you can create a matrix version of your more complex models. This can be very useful, when you have a 2 by 2 by 2 design, or you got like 7 predictors plus the intercept, and you don't want to be writing it out by hand. It's too much work. Or you have other models like multinomial processing tree models, and you might want to write those in matrix form if you have multiple predictors as well. Otherwise, it'll start to get really ugly. So as I said, the beta vector is now containing 3 elements. Beta 1, 2, and 3 are the 3 slopes, and you can extract all the information. So here are the 3 betas, the posteriors that you can see, and you can of course get each one of those out if you want to process them further by hand for some reason, right? Okay, so the next topic is logistic regression. And it's also just, straightforward extension of what we've done so far, but there's some interesting new details of Stan that you will see. So again, we are going to look at an old data set where we have set size and trial effects, and we want to know whether these two things, set size and trial, whether they affect the free recall, right? This is an old data set. So you got correct, incorrect responses in data points. We are assuming a Bernoulli, and this should be a probability. So we are back transforming with, the equivalent of P logis in R. We are back transforming the log odds values. It's in matrix form here, okay? So we got priors, slopes, everything. So again, now it's more compact because we define beta as a vector, okay, of size k equal to 2 because it's only 2 predictors. So the code looks like this. All this is familiar. We just did that. The only thing new is that the dependent variable correct has to be of type integer and not real, because it can only have values 0, 0 and 1, right? So we're going to create an array with n elements of type integer, okay? Here's the code again, matrix in a matrix form, and then we define the priors as before. And now what you see is the use of a built-in function, okay, in Stan that implements the p logis back transform for you, okay? So in the Bernoulli expects a probability, but we are doing everything in log odd space. This is all log odds, right? These priors are defined in log odd space, okay? So all this is internally being converted back to probability space so that we get back everything in probabilities, okay? So am I saying this right? Oh, maybe I misspoke here, because what it's actually doing is it's fitting the model in log space here. So I'm sorry, I misspoke there. So it's fitting the model in log space here. And then if you want to back transform, we can do that later on, right? Like I discussed earlier. Right. So the only reason to use these built-in functions is you get more efficient processing. But if you want to be more transparent, you could just take the log odds version of the transformation to log odds, fit the model in log odds space, and then proceed from there. Okay. And this is useful. Like not using the default thing is useful because you might want to define some nonlinear relationship here between the predictors and the betas. So in that case, one would use the standard function, the logit, Bernoulli logit. Okay. Um, there's a third way of doing this. Instead of using Bernoulli logit, which moves you into log space, you can use Bernoulli LPMF, and there the dependent variable is still 0 and 1, but we are wrapping the entire predictor, the intercept and the slopes, into in the inv underscore logit function. That inv underscore logic function is the p logis function in R. So there are three ways to do this here. Okay. So there will be an exercise on this where you can replace, this with some other link function. Okay, instead of using this inverse logit, you could use another link. So that's coming up later. So um, so what we are doing here is that for every element in the array, correct, incorrect, we are just filling in the um, we are defining the generative process, for the model here. Okay. So notice here that this is a matrix, but we are going row by row in that matrix. This is different from R, where if you wanted the nth row of a matrix, you would have to write in the square brackets n comma and then close square brackets, right? So that's different here. So so this would be, is this correct? Yeah, this is correct, because this is every iteration of this for loop would go like row by row, take the k predictors, k is equal to 2 now, multiply it with a 2 by 1 matrix, right? The beta matrix, that's a matrix multiplication. So that's what's happening here. Okay? So here we just fit the model and create the model matrix, blah, blah, blah. Standard, everything is the same here. Here we are again doing main effects and interactions. So there will be 3 predictors now. K will be 3 now, right? So I said K is equal to 2 earlier. So that would be the case if we only had set size and trial as main effect and no interaction. Okay, so now we can summarize the results. We got alpha and then the beta vectors. So you can see the 3 predictors here, the slopes, 3 slopes here, and the intercept here. So you can get the posteriors, right? And these can of course be back transformed back into probability space, right? So normally one would do this within R, right? So by extracting the samples for each of the parameters, and then back transforming it using that equation that I showed you, the p-logis thing, right? But there's another way, which is just to use the inverse logit function. So this is the p-logis transform back into probability space. This gives you the average accuracy. In the generated quantities block, you could write you could figure out, any for the 3 predictors, right? For the 3 predictors, we are going to figure out the change in accuracy when we go from what are we doing here? From the average to 1 step below the average, right? So alpha minus beta, right? So the change in accuracy as you go from the average to one step less than the average, 1 unit less than the average. Okay, so what we are getting now is the deterioration in accuracy when the subject is exposed to a set size uh, larger than average by 1 unit. Did I get this wrong? It says, I think could there be a mistake here that we are increasing the set size by 1 unit? Oh, right, right. No, there's no mistake here. Sorry. So what we're doing is by subtracting from the average, going 1 unit back, what we are doing is we are finding out the increase in accuracy or the change in accuracy when we increase the whatever the predictor is by 1 unit. Yeah, it's not wrong. It's correct. Yeah. So that's what we're getting here. But now we're getting this in probability space. Okay. So increasing the set size by 1 unit causes reduction in recall accuracy, right? Small amount of recall reduction, right? So one could have also done this like this, okay? You could have gone inverse logit alpha plus beta minus inverse logit alpha, okay? That would also tell you, but then you'd have to flip the terms, right? Put this one, the plus term, the term with the plus would come first, and then alpha would come second, right? So that would tell you the change from um, mean plus one to mean, or the change in accuracy, the change in accuracy going from mean to mean plus one, right? All right, so that's pretty straightforward. This is not different from anything that we saw in logistic regression. The only new thing now is the way that the models are defined. So I showed you 3 ways in which you could set up the model, and you could just keep it simple, and not get into any complications, and fit the model using the basic, whatever is more intuitive to you, either this statement here or Bernoulli logic LPMF. This would be also perfectly fine. I think for the data sets that we'll deal with, there won't be that much impact to, no desperate need to optimize. But in the future, you may need to refer back to these options. So that's the lecture on Stan. We will talk much more about Stan later on. These are the basic ideas for multiple regression in Stan that we wanted to introduce in this chapter.